is hydrochloric acid. HBr, hydrobromic acid. HF, hydrofluoric acid. These are all examples of acids, and they can have polyatomics tagged onto the end. So we saw H2SO4, sulfuric acid, and bases. Bases always end in OH. So if anything, NaOH, sodium hydroxide, calcium hydroxide, strontium hydroxide, all of these things end in OH, they're bases. And then salts are kind of, by definition, what happens when you react an acid and a base together. So if you end up with NaCl, that's a salt. CuCl2, that's a salt. Z, R, and F, zinc-chromium fluoride, those are salt. So these salts are this kind of broad category of elements that you get when you react a base and an acid together. So that being said, let's look at our analogies, and then we'll look at a couple examples. So I said, we'd get to where the water comes from, and this is where the water comes from. It's a double replacement reaction. So your metals are going to kind of switch. The trick here, not a trick, but the H is acting like a metal in your acid. So your H is kind of like a metal, and it's going to swap with the B. So you're going to end up with H and OH. HOH. What is that? Well, that's just a really funny way of writing water. HOH. It's H2O. You have two H's and an O. So it's really just a double replacement reaction. You have the B and the A are going to end up together, and that's your salt. So there's your analogies. Again, double replacement, same thing, just a little bit of a special one because you end up with this HOH. Let's look at a couple examples. If you really, I'll do one and then you guys can do the next one by yourselves because it's really, looks kind of messy. It's not terribly difficult. All right, so here we are. These are our neutralizations. Neutralization type reactions. HBr, NaOH. All right, so we've decided that the H and the Na are going to switch partners. So I'm going to end up with HOH, which is just a funny way of writing H2O. You can think of it as H and an OH. That's exactly right, Abby. There's no, if you're doing it, you see two compounds to start, it's a double replacement. The only sort of catch to your logic here is that if you're asked to identify the type of reaction, it's important to know that this is a special type of double replacement. So you're looking at a neutralization reaction. So although a neutralization reaction is technically a double replacement reaction, it's a special type. So you would be able to predict the products correctly for sure. But if it asked you to identify it and you said it was double replacement, we're looking for a little bit more specific. So a neutralization is a special type of double replacement reaction. So you end up with this HOH, that's just water, and then what's left is your Na and your Br. So you're gonna combine together your Na and Br. And by definition, if you have an acid and a base react or neutralize one another, you're gonna end up with a water and a salt. Sodium's always +1, bromine's always -1. NaBr is going to balance out. We end up with NaBr. I guess the important thing here is to remember to put your metal first. You don't want to end up with BrNa. That's not good. So you don't want to run that risk. But there you go. Special type of double replacement, which we call a neutralization. As soon as we see an H to begin and an OH to end, we know we have an acid-base neutralization. see what you can do with this one, the second one down at the bottom here. And we only have one type left, which is kind of nice. So see if you can figure out what type of salt you're going to have, and then what's going to happen with the H and the OH. Let's give you a second to do that. If you're feeling brave, you want to throw it into chat, haven't really spoken up yet, this would be a great opportunity to check your compound forming skills. All right, this is a bit of a trickier one. I mean, it's not terribly difficult, but it isn't super straightforward. So hopefully you've just attempted it. See what you ended up with. So if we take the H and the OH and we put it together, and again, you don't want to get caught up with the H had a 3 next to it on my reactant side, and the OH, there's 2 groups of that on my reactant side, so how many waters am I going to end up with? That's a problem we're going to deal with when we balance it later. So don't get caught up in the H3, OH2 sort of thing as the reactants. You don't want to get thrown off by that. It's important to recognize that you're combining H and OH together. That's going to give you water. So we have H2O. And then we have the Mg and the PO4, magnesium. Yep, we started with 1, but it doesn't matter. Magnesium is always +2. PO4 group is always -3. So I'm going to separate these with a plus sign. And I'm going to end up with Mg3PO4. And because I have more than one of that group, I have 2 of the group, I put it in brackets so I don't get confused and write PO42. And Anna, you were on the money here, H2O, Mg3PO4, 2. So that's terrific, because that's a bit of a trickier one. That's kind of as messy as they'll get, that one right there. The last type we're going to look at is a combustion reaction. And combustion reactions are gifts. You know how I said, oh, you get a covalent type question? It's kind of a gift. That's what's going to happen with your combustion reactions, because they're really obvious. And predicting the products is always the same. So when you guys see a combustion reaction, you're going to be really thankful, because they're really, really easy to deal with. Hard to balance, easy to deal with in terms of the type of reaction. So a combustion reaction is the last type we're going to deal with. And combustion reactions occur when you have a compound or an element and it reacts with oxygen gas. So for the purposes of this course, combustion reaction will always have a hydrocarbon, hydrogen, carbon, hydro, carbon. So hydrogen and carbon in some combination reacts with oxygen gas. The beauty of a combustion reaction is the products are always the same. Doesn't matter which hydrocarbon you burn, if it's gasoline, candle wax, anything. Doesn't matter what you're burning, you're always going to produce carbon dioxide and water. So you can talk about burning methane, CH4, swamp gas, methane, natural gas, and combining with oxygen, so CH4 and O2 produces carbon dioxide and water. That's it. Acetylene is a type of hydrocarbon. It has ethane in it, and C2H2 is acetylene. Doesn't have ethane in it. Sorry, C2H6. So acetylene, C2H2 plus oxygen gas gives you carbon dioxide and water. Carbohydrates like glucose, C6H12O6 plus O2 produces carbon dioxide and water. So we always end up with the same products. It's a specific type of double replacement. It doesn't really work out if you're switching partners because these ones are bonded covalently. So you're going to end up with a hydrocarbon to start with and oxygen gas. So there are going to be no other, I shouldn't say that. If you see oxygen gas, it's probably going to be a combustion. It might be a single replacement type reaction. But if it has a hydrocarbon and oxygen, then you know it's going to be a combustion type reaction. So not another type of double replacement because these are all covalently bonded. You're going to have C something, so the X is just replacing a number, and H something. If you have a hydrocarbon, C and H, and oxygen gas, you know you're going to produce carbon dioxide and water. Specific example, CH4 methane gas plus oxygen produces carbon dioxide and water. So let's look at a couple examples. These are going to look like this. C4H10 plus O2, what is that going to produce? C3H8 plus O2, what is that going to produce? Now, I said these are gifts, and they really are when you get these on your tests, because you're always going to end up with CO2 and H2O. CO2 and H2O. That's it. Just CO2 and H2O. It doesn't really matter what you're starting with. You're going to end up with CO2 and H2O as your product. All the time. I could make up some hydrocarbon. It probably won't be a stable one, but I could have like C36H, I don't even know, 80 something plus O2. What happens? Well, I'm going to end up with CO2 and H2O all the time. That's not a stable hydrocarbon, so ignore that. But that's what it's going to end up like. Always going to have the same products, carbon dioxide and water. Anytime you burn a hydrocarbon, you're going to end up with carbon dioxide and water being produced. That's it. So what I want to do is probably just take a little break here. Maybe we'll look at some examples from the learning guide after the break. And then I think I want to talk about reaction rates because we might as well just get all of chapter 6 or unit 6 done all in one day. I'm pretty sure that's it for slides. Yep, that's it for the notes. So before we go for break, does anybody have any questions about types of reactions? We'll look at a few more examples, but they're all there. So you have a synthesis reaction where you start with two individual compounds, they combine together, decomposition, one thing breaks down, single replacement, double replacement, and then the two special ones, neutralization and combustion. Nobody had any questions, which is good. It means I've done an excellent job of describing all of these things for you, or you're so lost you don't even know where to begin. Let's hope it was an excellent job. It is about 10 after 10. Let's maybe take, very small unit, Anna. Let's maybe take 10 minutes, and I'll meet you guys back here in 10. So grab a drink, grab a snack, get up, move around a little bit, get the blood flowing, and we'll see you guys in 10 minutes. Thanks. Hi guys, welcome back. If you can give me a green check mark and let me know you're with me, and then we will carry on. So I just want to take a look at the learning guide first, and then we might get through the second section, which is really quick. I just want to see if this loaded. It did. Fantastic. Thanks, guys. All right, so we've gone through the types of chemical reactions. They're single replacement, double replacement, synthesis, decomposition, and then neutralization and combustion. So those are your six choices. For the learning guide, the part that you're going to fill in, Unit 6.1, basically it has some just, brief sort of summaries of all the different types. And then there is a bunch of classify the following reactions as synthesis, decomposition, double replacement, single replacement, neutralization, or combustion. And then it says, if you want extra balancing practice, then also balance the reactions. I want you guys to have extra balancing practice. So for number 2 on your learning guide, I'm not even going to guess as to what page it is after the kerfuffle we had last time. I want you guys to balance. And what that means is that you will have to do the work on a separate piece of paper, unless you can write really, really small and you can fit H and O in here and H and O and then balance. It's going to get a bit trickier with some of the bigger ones. But if you feel you have enough room there, good. If you don't have enough room, do it on a separate sheet of paper and include that when you submit it. For the first part, like including the descriptions here, for question 1 out of 6.1, is that what you're talking about, Abby? I'm not concerned if the examples you use here are not balanced. That's fine. Don't worry about balancing question 1. So don't balance question 1, but question 2, when it asks you to identify the type, and then it gives you little blanks to balance it, please balance those. So I'm talking question 2 here, balance them. If you can fit them in, awesome. If you want extra room, do it on a separate sheet of paper, staple that onto the back, submit it. That would be great. Maybe let's do a couple of these and then we'll move on to the last section, which won't take terribly long. I'll let you guys balance them, but for now I just want to talk about the types of reactions. So with practice, you'll get to understand and you get to see that things happen again and again and again. That's why we classify things. All country music sounds relatively the same. Why? Well, it has the same sort of ingredients each time. Rap music, same ingredients. Pop music, same ingredients. We've classified music. Now we're classifying reactions based on kind of what's going on in them. So as soon as I see like 2A, I see that there's only one reactant. There's only one thing to start with. So if you only have one reactant, what options do we have in terms of identifying the types of reactions here? You don't really have a lot of choice. I believe in your notes, I'm just going to scroll up. No, we didn't include the little summary chart. All right. In the course, I might as well just go find it right now while we're here. In the course notes that kind of go along with your fill-in-the-blank notes, there is a little summary chart that I want to look at. Use my mouse here, scroll down. So we did types of chemical reactions. And give this a second to load. Summary of reactions is down here. Give that a second to load. Basically, it's a chart that has... Maybe it's not in here. Why did I think it was in here? Excellent review of the types of reactions. No, no, no. All right. Maybe it's at the top. Anyways, there's a chart. I'll find it. I'll include it in the course so you guys can have it. That has a summary of all the different types of reactions all in one spot. I'm sure it's somewhere in here, but I'll find it and have it for you next day so you guys can have it. And basically it just has all of the sort of the descriptions that we've gone through thus far, all in one spot. So if you're starting with one reactant, only one, what type of reaction must this be? Does anyone want to throw it into chat? And using the abbreviations like you're doing there that's fine by me. We don't need to be too terribly fancy when we're doing this sort of thing. So DEC, that's great. That'll work. It's at the bottom of the last question for 2. Anyways, I'll find it. And it's there somewhere. Decomposition is right. You can only start with one thing if you are doing a decomposition reaction. That's what's happening here. And H2O2 is actually hydrogen peroxide. This is the example that we did in class. The next one is kind of obvious, but it's not until you've gotten lots and lots of practice at it. But it starts with 2 compounds. So if you're starting with 2 compounds, you're either going to be a double replacement, you're going to be a neutralization, or you're going to be a combustion. So in this case, I see that I have an H to begin with and an OH to end here. So this is a special type of double replacement. So I don't want to write double replacement. I'm going to write neutralization because I'm starting with an acid and a base. How about this next one? Letter C. What do we think? Anyone want to take a shot at that one? You have aluminum and you have nickel bromide. What's going to happen here? What are our choices? So really we're starting with a single element and a compound. So we've got single replacement and we've got a vote for double replacement. Does anybody else want to support one of the others? Do we have a tiebreaker? Or we can think about what's going on here. Can we start do we have the right ingredients sort of thing for a single replacement, or do we have the right ingredients for a double replacement? So for a single replacement, we're going to have A and something like a compound. Is that what we have here? We have an element by itself and a compound. The aluminum looks like it's kicking the nickel out. Now the nickel's by itself, and then we have the aluminum and the bromine. So this is a single replacement because the aluminum kicked the nickel out. So that's why that's a single replacement. Let's do letter D, and then I'll leave the rest for you guys to do later on. Letter D, we have nitrogen and hydrogen. These are 2 diatomic elements when they exist by themselves, N2 and H2. And then those are combining together to give us NH3. So we have 2 individual elements combining to give us a compound. Anytime we end with one thing, we know we've had a synthesis reaction. We're synthesizing 2 elements together to give us a compound. So that is the types of compounds. I want you to balance those. So you'll have to go back and do the first 4. I want you to, more importantly, be able to identify each one of those reaction types. So I'll give you guys that to do for homework. And what I would love to do is jump into 6.2. And there you go, Taylor. Thank you for identifying where that table was. This is what I was looking for. You can see that it gives you basic breakdown of each one of the types of reactions, and it gives you some like not like words, it gives you words to kind of describe what's going on. So if you start with two elements combining, you end up with a synthesis. One reactant only, decomposition. One element and a compound, single replacement. Two compounds, acid plus base, organic compound with oxygen. So a quick summary of everything that we did in that big long hour that we just sat through. So there you go, a nice easy way to be able to identify all of the types of reactions that are taking place there. So there you go, it goes up to Y. I want to jump into the next section so we can kind of cruise through this. We're actually going to encounter this again next week. This is the lesson that I'm going to go to KSS and do. I'm not sure when exactly we will end up at KSS, or I will end up at KSS, and I'm going to broadcast from KSS, but it'll be this lesson. So friend of mine, Mr. Wilkinson at KSS, he's a little bit behind where we're at. So this is where he is going to be next week. So we're going to jump into it now. You guys will be experts by the time you see it again. And what we're going to do is just a bunch of demonstrations based on some of the ideas and concepts we're going to discuss here. So rate of chemical reactions, this is unit 6.2. And really quick section, so we'll get it done in the next 30 minutes or so. And you guys will be ready to go. So reaction rate. Often, this statement's really true. Often controlling the rate of a chemical reaction is as important as having the reaction occur in the first place. Some reactions occur really quickly, and they can happen so fast that you can't even see what's going on. Some reactions can happen so slowly that it takes very long periods of time for the reaction to occur. And for us to observe it, that's not really helpful. So if we can control how fast or slow a reaction proceeds, we can kind of learn more from the reaction. So it is very important. Anyone think of why we would want a chemical reaction to take place really fast? What would be sort of an example of somewhere where you would hope a chemical reaction would go really quickly? Anyone think of any examples of that in your everyday life? And chemical reaction is really broad, right? There's literally billions of chemical reactions going on inside your body right now. Around you, there's chemical reactions happening everywhere. It's kind of like this big idea, right? But why would we want a chemical reaction to take place quickly? Or can anyone think of an example of something you would like to happen really quickly? Yes, in a science experiment, so we don't have to sit and wait for a long time. That's funny you should say that. When you make it to, if you make it to university chemistry, you do something called acid-base titrations, where you try to neutralize an acid and a base, and based on the volume you use, it tells you the concentration of the acid. Anyways, long story short, when you're doing the reaction, you have this long pipette, and you just open this little valve really slowly, and it just drips and drips and drips until the color of what you're dealing with changes. And when the color changes, you're done. So you can literally sit there pouring in the liquid really slowly, a drop at a time, and it can take forever, and then the color changes and you know how much you added, so then you're done. But if you go too fast, you get too much in there and the color changes and you don't know exactly when it changed because you just added a bunch at a time. So it was really frustrating. I had to do it like 3 or 4 times one lab, and that was an example where I wish the reaction would take place a lot more slowly. So why would we want a chemical reaction to take place quickly? An explosion is what Taylor said. And you might be thinking, well, we don't want explosions to happen in the first place, but there are lots of explosions that you want to happen all the time. When you're driving your car around, or your parents are driving you around, if the explosion of the gas in the cylinders happens really slowly, well, then your engine doesn't run properly. So that's a great example. This is what the textbook says. So to make a reaction happen quickly, these are the things you can do. And we'll look at all of these more in depth in a second. But for now, you can increase the temperature You could increase the concentration, you could increase the surface area, or you can add something called a catalyst or an inhibitor. So that's just a basic summary of what we're going to sort of discuss in the next few minutes. That being said, we talked about something happening quickly. We had the example of an explosion. Can anyone think of something in terms of a chemical reaction that you would want to take place slowly? Something that you encounter every day, possibly. What types of chemical reactions do we want to happen slowly? Is there anything in your life that is undergoing a chemical reaction, but you're like, oh no, I don't want that to happen. I wish it would happen slower. Maybe making sourdough bread. I don't know much about making sourdough bread. I assume it has something to do with producing some sort of gas with yeast or something like that to make it rise. If it happens quickly, do bad things happen? Maybe the bread will be really dense because you don't have all those little air pockets in there. Is that kind of where we're going with that? Not much of a baker. I like that example. So to just generalize your example, Abby, maybe in cooking, you want things to cook really quickly. That's a chemical reaction. You're changing what's going on there. So cooking would be a good example. How do we prevent things from happening quickly? Slow rise is better using yeast because it's easier to digest. Yeah, I was off, but that makes sense. Can you think of any other examples with food where we would want a chemical reaction to take place slowly? Does anybody have a refrigerator in their house? Anyone? Anyone at all? Why do we put food in the refrigerator? Why is it advantageous to keep food cold? Anyone ever think about why we do that? Pop. Like you don't want the carbon dioxide to escape too quickly. That's an example for sure. So why do we put food in the fridge? Why do we freeze food? Why does something like, milk? Why do we put milk in the fridge? Anyone ever thought about why you have a fridge in your house? Slow down decomposition. Is decomposition a chemical reaction? Sure is. So it doesn't go bad. Perfect. That's a chemical reaction. Food going bad, food rotting is a chemical reaction. Vegetables are covered in bacteria. You put it in a fridge, the bacteria starts or doesn't break it down as quickly. So we put things in a fridge where it is cold to slow the reaction down. So a fridge is an example of something you use in your everyday life to slow a chemical reaction down. If you just leave food out, it goes bad in the presence of bacteria and all sorts of other things that are there. How about your car? I can always relate to cars. Does anybody have like a rusty old car that maybe your parents gave you or something like that? Rust on your car is an example of a chemical reaction. You have oxygen in the atmosphere. Your car is made of metal, which has a lot of iron in it, and the iron rusts. Iron oxide, that is what rust is. So I don't want my car to rust, so I wash it lots to keep the paint in good condition and protects the metal so it doesn't rust. That's the reaction I want to happen really slowly. So that's another example. So if you want a reaction to happen slowly, it's just the opposite of the things that you want to do to make a reaction happen quickly. So instead of increasing the temperature, you're going to decrease the temperature. Instead of increasing the concentration, you're going to decrease the concentration. If you were to increase the surface area, you would decrease it to slow it down. And if you were to remove a catalyst or add an inhibitor, that would also slow down your reaction. So, here's two examples. Airbags in cars are kind of misunderstood. People often think that there's like a pressurized container of gas somewhere in your car that inflates the airbag, but it's actually a chemical reaction that's occurring. So, you see behind me, One airbag is inflating on time, and the watermelon gets cushioned by the airbag. And then the other airbag is inflating 1/100th of a second too late. And that watermelon isn't having as good of a day as it did on the other side. So this is an example of why you would want a chemical reaction to happen very quickly. Airbags in your car. If the reaction takes place too late, all of a sudden your face is hitting the steering wheel, and then you have literally an explosion happening in your face. Not a good thing to happen. So we kind of take for granted these things sometimes. I bring it up. This is how airbags work. Basically, you have a sensor somewhere in your car, and it says, oh, you've been in a crash, so I should make a chemical reaction happen. You have something called sodium azide, which is something that produces nitrogen gas when it breaks down. It happens very quickly. In literally like 1,000th of a second, that airbag starts to inflate. So it's kind of incredible that it's not compressed gas that's inflating the airbag. It's actually a chemical reaction. The sodium azide is actually producing nitrogen gas. So yes, that's how your airbag works. A lot of people don't understand or know or care. Your brother had that happen to him. Hey, Taylor. Yeah, it's pretty common. Car manufacturers are now starting to realize that airbags are inflating really quickly, and that can do bad things to people. So they're trying to figure out ways to slow down the airbag inflation so they're not exploding into people's faces at the same time as providing protection still. So it's kind of a fine line. Do you want the airbag to be there? Yeah, you do, but you don't want it exploding when your face is really close to the steering wheel. And there's lots of examples of how that can happen in bad ways. And Taylor, you've just proved that. So temperature. Think about temperature. I forget what grade you talk about the kinetic molecular theory, but talk about adding energy to particles. They vibrate, right? So you have a solid, you can see beside me here, solid particles just are in this little lattice structure and they vibrate back and forth really quickly. If you add some energy, they speed up a little bit, then they turn into a liquid, and then you add more energy, they start going really fast, and they're a gas. And all sort of substances that we have will exist in solid, liquid, and gas form, depending on how much energy you give it. So if you want a reaction to speed up, if you increase the temperature, you're adding energy. You're making the molecules move faster. The faster they move, the more collisions they have. The more collisions, the more reaction that's going to occur. So if you want something to happen quickly, by adding energy, by speeding up the particles, by adding temperature. Remember, temperature is just an average of the energy of the particles in that substance. The more chances of bumps occurring, and the more bumping you have, the more collisions you have, the more reaction is going to take place. So if you wanted to slow a reaction down, you could cool it down. You're taking energy out of the system. The reaction's happening slower because less collisions are taking place. So higher temperature, faster the reaction. Slower temperature, slower the reaction. And we get back to the idea of the fridge. If you are going to put food in your fridge, why does that help? Well, it slows everything down. Less collisions, less reactions, longer your food lasts. Cooking food, same idea. You add a bunch of heat to food, it cooks quickly, that kills the bacteria, produces new things that we like. You don't want that to happen over several days. Just making a meal would not be that fun. So that's temperature. That's what we can do to speed up a reaction. Concentration. Concentration talks about how many molecules there are in something. You can have a really high concentration. Now, the best example I can think of is making like iced tea or juice or something. So if you had a glass of water, and then you take your powdered iced tea mix and you put a tablespoon, or make hot chocolate or something like that. Put a tablespoon in, you stir it, and you take a sip, and you're like, that's not sweet enough. So you want to add more powder until it gets sweet enough. You're increasing the concentration, or adding more sugar, essentially. So if you think about adding stuff, the solution becomes more concentrated the more you add. So if you were to add this little solid, it dissolves in the water and you end up with a solution. The more concentration, same idea. The more opportunity there is for collisions to happen. So if you want lots of collisions to happen, you have a lot of concentration, that's kind of what you're looking for. Or you can do the opposite. You can reduce the concentration. You can dilute it more. You can add more water, make it less sweet, and less collisions will occur. So you have a slower reaction happening as a result. So that's how concentration affects reaction rate. Surface area. The more surface area you have, the more opportunities for collisions to occur. So if you take if you imagine like a sugar cube is full of sugar, but if you were to put your sugar cube in your tea, the only place the tea is touching the sugar cube is on the 6 sides. You have 6 sides. Well, what if you took that sugar cube and you crushed it up into a powder, and now have you increased the surface area? Yeah. Now you have a lot more area to have sort of collisions occurring. So behind me here we have one big cube, and then if you took that cube and you divided it into smaller pieces, now instead of having the 6 sides for this surface area, you still have the 6 sides, the top, the bottom, the left, front, back. But now you also have these additional surface areas in the middle, so you're adding more surface area. Now if you took these cubes and broke them down into 4, you still have the original surface area, the 6 original sides. You still have these sides from these cubes, but now you have a bunch of additional sides up these gaps in the middle. So by breaking a solid object down, you are increasing the surface area. And sometimes students have a difficult time wrapping their head around how taking a solid and completely crushing it into a powder increases the surface area. But it does. Just think about that one sugar cube, and then you cut it in half again. Now you have 4 smaller sugar cubes. So you still have the original area, but a bunch of additional area. You cut those smaller. You could keep doing that until you end up with just a really fine powder. And those tiny little sugar grains, you could reassemble back into one big sugar cube. And each one of those grains, you imagine, had 6 sides. You've increased the surface area a lot. The best example I can use to describe this is medication. I think it's a pretty good example. These red dots are showing sort of collisions occurring. If you have one solid object, all of these molecules in the middle here, they aren't taking part in any of collisions. Just the outside is taking place in collisions. So all of these are kind of hidden. You're limiting how much you have. But if you broke up the green into all of these smaller pieces, now you have all sorts of surface area. Now there's almost every single one of those molecules is now exposed to a collision. If you crushed your house into a powder, would it still increase surface area? I'm not sure I understand where you're coming from or going with that, but yes, I'm not sure. I'm kind of picking up what you're trying to get at there. The example I use in medication is this. If you get some medication that's long-lasting, say you have a cold, you go to the pharmacy and or you have a headache or something. Long-lasting pills come in these little tablets. Why? Because they have a very low surface area and your stomach kind of dissolves them over long periods of time. You're only going to have that outside sort of acting. If you want a fast-acting medication, they usually come in these little capsules. And when they get into your stomach dissolves the capsule outside and all the powder gets released and it acts really quickly. So long-lasting medications will be in these tablets. Fast-acting medications will almost always be in capsules. And inside the capsules, there'll be a fine powder because your body can absorb that much more quickly than it can here at eroding the outside surface, like one atom at a time sort of thing. So that's a a pretty good example of, at least in my opinion, on how you sort of encounter these sorts of ideas in everyday life. Surface area, put in a capsule is powder, dissolves. Gel, same idea, great example. So gels are liquids, and sometimes that's what we'll do. It kind of gets back to the idea of concentration. Liquid is even better. It can get dissolved even faster because it doesn't have to dissolve the solid into any liquids in your digestive tract. So I have these, I don't like taking pills, but I have, I think they're Advil cold and sinus. They have like a sugary coating on the outside, and I don't mind it. But some of them they do taste pretty bad. I guess you're an adult when you're taking, medications that don't taste good anymore. Not like when you're a kid and everything had to be covered in sugar to make it palatable. The last thing is called a catalyst, or an inhibitor is the opposite of a catalyst. Now, catalyst is a general term that we deal with in science. If you're talking about an organism, so anything that's living, so living systems don't use catalysts. They use the exact same thing, but we call them enzymes. So a catalyst and an enzyme are the same thing. If we're talking about your body, you're dealing with enzymes, or any animals, things like that. If you're talking about sort of chemical processes, you're talking about catalysts. So same thing, they do the exact same thing. And what they do is they help bonds form, or they rearrange molecules so they can combine together more quickly. Now, remember when I did the elephant's toothpaste demonstration? It was hydrogen peroxide, H2O2, and it broke down into water and oxygen gas. What did I do to make that happen really quickly? I added something called potassium iodide, and potassium iodide is just a catalyst. It didn't actually take part in the reaction. It wasn't H2O2 plus Ki produces these other things. So catalysts don't take part in the reaction. All they do is kind of arrange things so the reaction can happen more quickly. And an inhibitor is the exact same idea, it's just the opposite. It makes it really difficult for the reaction to occur if you want a reaction to happen more slowly. So the tricky thing here is it doesn't actually participate in the reaction. It is there, it's present. So I took the hydrogen peroxide, I dumped in the potassium iodide. It was there, they mixed together. But in terms of a chemical reaction, the potassium iodide didn't actually react. It just helped the reaction occur. And there's a really interesting picture here behind me about how enzymes work. So this is kind of a really simplified idea of how you can get an enzyme to work. So let's say you wanted these four things to react. So you had these two little yellow guys and these two red guys, and you wanted them to all combine together to produce this new thing here. Well, this is the enzyme. It basically has on its surface, or some other way, it has spots for these things to fit together. And when they fit together, they can combine, and then they produce this new thing. So you can see how the enzyme isn't actually part of the reaction. These are your reactants here, or catalysts are the same thing, right? These are your reactants, and this is how you want them to combine together. If they were just left to chance out here, they might not combine perfectly in this manner. Their backs might bump into each other and they wouldn't combine. Things like that could happen. But when you add an enzyme or a catalyst, it lines everything up. It makes those two reactants come together in a way that they're going to combine together. So the enzyme isn't actually taking part in the reaction, it's just there to help things move along. So that's how an enzyme or a catalyst works. The example we have here in the notes is salivary amylase, which is it's produced in your mouth. And when you're in grade 8, I think you talked about body systems, and you might have actually done this. And if you haven't, it's kind of interesting. If you take a piece of bread has really long carbohydrate chains. If you break down carbohydrates into smaller and smaller pieces, they turn into sugars. So if you were to take a piece of bread without chewing it, you just put it in your mouth and you leave it there. When you initially put the bread in your mouth, it's not very sweet. But if you were to leave it for, several minutes, the salivary amylase that your mouth is producing, it starts to break down those really big carbohydrates into sugars. So the bread that's just sitting in your mouth will actually become sweet. So that's an example of what an enzyme does in your body. And you have, I don't even know how many thousands, if not hundreds of thousands of enzymes in your body that help reactions take place. That's just one that is pretty common. Another one you might have heard of if you're into cars, I'm always into cars, is catalytic converters. So we talk about a catalyst, catalytic, same idea. Basically all new cars that are made, if they're a gas-powered car, they have a catalytic converter in the exhaust, and it's kind of like a honeycomb